Yes, so recording is going and my video is going. Hopefully my laptop doesn't mind so many things running. Right, hello everyone, welcome. I'm Joshua, I happen to be Vice President of ACM, and today I'm giving a talk about Rust. So, what is Rust? Rust is a programming language, and the interesting thing about Rust is to see like the good parts of Rust, you kind of have to see what it's reacting to, because Rust in many ways is kind of trying to address flaws in other languages that it's seen and make those easier to work and to program with. So we're actually going to start this talk by saying what Rust is not and saying the problems it's trying to address. So of course it's trying to address memory safety, it's trying to address thread safety, and it's trying to have stability. So what do all those things mean? So memory safety, if you've ever used C or C++, you know the compiler gives you absolutely no help. Like if you want to dereference a null pointer, it says, okay, go ahead, kid. Like that's fine. And you get like out of bounds accesses, you get use after freeze, and like in the best case scenario, you get a segfault. In the worst case scenario, you get like random data in your program. And now you don't know what it's doing anymore because it's at like a random address in memory. So have fun with that. That's normally how you get vulnerability exploits. Anyway, I have a whole talk about this, and the whole talk is about why just program it right doesn't work. But that's not what I want to talk about today. I want to talk about the alternative to that, which is the borrow checker, and we'll talk about that a little later. And the next thing Rust tries to address is thread safety. And if you haven't heard of threads before, threads are a way of executing multiple pieces of code physically at the same time, like on two different cores on a CPU. And so the issue there is if you have code that depends on the order it's run or has like shared data or shared memory or things like that, then you have to sequence that yourself as the programmer. And the difficulty there is how do you know you did it correctly? And in most languages, it's really hard to do. So thread safety is interesting to me because it's an unsolved problem in most other languages. Like if you want memory safety, you can use Python or Java or JavaScript or whatever. Like all those, like because you don't have raw pointers, you just don't have segfaults. But for thread safety, you don't have languages that help you with them very much. So one example I want to give here is in C, one of the most broken APIs is error number. So in C, if you're like trying to read or write to a file and an error occurs, what the function will do, like the read function, is it will return like -1 or something, which says an error occurred. And if you want to look it up, you have to look at this global variable called error number. And so the issue there is if you have multiple threads, like one of them reads a file, another one reads a file, they both fail. How do you know which thread the error belongs to? Like you don't, like it's just one variable here. And so GNU had to like completely redo their threading model for this. They had introduced thread local storage. It's a whole mess. And the problem is it just wasn't designed with threads in mind. And even more so than that, sorry, go ahead. What, sorry? A thread is like a way of executing multiple pieces of code physically at the same time. So you have like this piece of code running and this piece of code running, and they're literally both running at the same time. And so it's very easy to design libraries that are not made with threads in mind. And if you try and use them with threads, in most languages, it will work until it doesn't. And when it doesn't, usually it works very badly. And so the last thing I want to talk about is backwards compatibility. Rust has a slogan, stability without stagnation, because it's very hard to do both. Like either you can have a very stable language like C, which hasn't gotten features in years, or you can have a language with lots of features like Python or C++. But the danger of having lots of features is it's hard to change them after they already exist. Like C++ is basically three languages in one. It's C, and then it's like old C++ with like new and delete, and people say, oh, don't use new and delete, use unique pointer, which is like new C, and it's a whole thing. And the problem with that is you have like all this code that's existed for ages, and so you can't get rid of the features you don't want anymore. They're stuck in the language forever. Python has the same issue too. I don't want to pick on C++ too much. It has like 3 different ways to do web scraping just in the standard library. There's URL-lib and URL-lib2 and URL-lib3. And so there's a saying in Python, the standard library is where modules go to die because they don't get much development after they're in the standard library. Yeah. So these are the main things that Rust are trying to address, is these three problems. So let's talk about how it does that. Right. So now that we've talked about what Rust is, we're going to talk what Rust isn't. We're going to talk about what it is. And this is like from the Rust homepage, which I have over here. And so I love this comic because everything in Rust is about like protecting you at compile time as much as it can. Rust users want static verification. I love this article. Here it is. Literally, they put it in caps. Like this is a big thing in the Rust community. We want to catch as many things at compile time as we can, because if things happen at runtime, then that's how you end up with like bugs and like 3 a.m. Oh, the site went down. I have to fix it. So some of the ways that it does that, and there's a whole bunch more. These are just like the main ones that came to mind. Is it has type safety. It has memory and thread safety at compile time. And you can do crazy things like type state, which, I don't want to talk about type state too much because it's like an advanced thing. But you can actually say, okay, you have to use this library correctly or your program won't compile. In most languages, this is documentation. In Rust, you can like actually enforce it, which is very cool. Yeah, this is a long article. I'm not going to go into it here. All right, so type safety. So everyone here has used like either Java or Python or JavaScript, I assume. And so in those you have null, and null is, okay, there's nothing here. And if you try and call a function on it, it'll give you a null pointer exception, and it'll say this object is null and it doesn't have methods or whatever. And so in Rust, null is not built into the language. Null is a type that's in the standard library. And the thing about that makes it really useful is that the compiler can check at compile time whether a value is null or not. And so if you forget to check for null, like you try and use it without checking first, the compiler can say, oh no, this could be null, you have to check. And the really useful thing about that is you don't have null pointer exceptions anymore. Like they're just, I say that, but there's a function called unwrap, which is basically like I don't want to check. But it's a lot more rare. And the real difference between that and null in Java and JavaScript is that not everything can be null. Like there are values that are known not to be null, which is really useful property. Like instead of strewing null checks all around your program, you put them where they belong, and the rest of the program can assume the value is not none. None is the equivalent of null in Rust. And the other thing that putting it in the standard library makes really useful is to add like functions that manipulate null and like have syntax around it. Instead of having syntax like you would in JavaScript, like there's this like Elvis operator, I think it's called, which is like give me the value if it exists, otherwise, oh, well, Google's not cooperating, hold on. But basically this says give me the value if it exists, otherwise if it's not null, otherwise give me some calculated thing or whatever. So in languages with null, you have to have syntax for this. You can't like have a function that's as convenient as this because null is in the language. Like you have to have an if everywhere. In Rust, you can have it as a function. So this and then is basically that Elvis operator, but it's just like a function implemented on option. You can have like a bunch more functions here, like all these are various things you can do with option. And so it's extensible in a way that null really isn't, because syntax is hard to add, because it's usually breaking change when you add it. And so this code probably looks foreign to you because Rust syntax is odd, but I'll explain, well, I'm not going to go too much into the syntax in this talk, because this is more like why would you use Rust rather than how do you use it. But this is actually real code. I found this in like the Cargo build tool and stole it because it looked neat. And I like this quote. So Rust takes a lot of its type safety from Haskell. Haskell is like a real functional programming. We're going to make everything types language. And this is a quote I found, which is we're going to make, everything types so people learn to use them without learning Haskell. Anyway. And so the other cool thing that Rust has as part of the standard library is result. Result is like an error type. Either it worked or it didn't, and those two variants are okay or error. And the interesting thing about result is you have to check it, the same way that you have to check option, and you can't just ignore the fact that it's null. And so what that gets you is you can't keep going after an error and use values that are uninitialized. And I'm picking on Go here because Go does let you do this. So here's like a Go playground. Here's a program. So this is the original from like the Go error handling page, right? Here's a file, open it. If there's an error, like log a fatal error and quit. Otherwise, do something with the file. And so the issue here is Go lets you just omit those error checks. Like, if I take out those error checks and I just don't write them, this program will run. It won't do anything useful, but it will run. If you look here, it printed like the default value for an array. And so Charles is about to yell at me because he's going to say, oh, well, why did you ignore the error? You told the compiler to ignore the error. That's bad. And yeah, it is bad code. But the fact that I can use values that haven't been initialized and just ignore errors is slightly concerning. I mean, it worries me a little. There's a blog post that talks more about this. This guy writes really good blogs. I highly recommend his stuff. Yeah. Oh, wrong chat. Too many things open. Okay. Right, and so this is not unique to Go. You can do this in C++, you can do this in C, but it's a semi-common problem. And so HTTP is a really interesting example here. This is a Rust HTTP library, and so in most libraries, if you get like a 404 or something, the library will give you back, okay, you got a response, and if you want to like look at the body or whatever, you can do that. But it doesn't throw an exception. It saves exceptions for like I/O errors and that sort of thing, which has the same issue that I was talking about with the Go code, is you're looking at the stuff uninitialized. And normally what happens is you like expect JSON or something and you get back an error message and your program crashes because you try and interpret it as the wrong thing. So I thought that was an interesting analogy. Feel free to ask questions as I go, by the way. I know that I tend to move very quickly. So I want this to be a talk that people are learning, not just me talking. Right, so the next thing I want to talk about is memory safety in Rust. So Rust kind of takes a unique approach here. The existing approaches are C and C++, which is just no memory safety at all. Like it's your job as the programmer to make sure things don't go wrong. Or there's languages like Java and JavaScript and things that run in the VM or that are garbage collected and don't give you raw pointers, and basically you don't have the option to do things wrong. And normally there's a runtime penalty for that. It's either there's like everything has to be boxed like in Java, or there's garbage collection, or something that because the compiler has overhead, or not the compiler, sorry, the runtime is overhead. Okay, since you don't have raw pointers, we have to do extra like bookkeeping to make sure things are freed eventually. Rust does not do either of those. Rust instead has a borrow checker. And what a borrow checker does is it says we're going to enforce like certain usage patterns that we know can't cause memory corruption. So for example, if you try and use something after it's freed in Rust, that's a compile error. Like at compile time, it will say, okay, this doesn't work. Let me try and find that example here, because it has, yeah, here we go. It says, okay, the value is moved here. You try and use it after the value was dropped, which isn't allowed. And I do not know another language that does this. I think there's like a research language, Cyclone, from the 1980s, but no one ever used it. Rust is like the only major language I know that does this. Yes, go ahead. Right, so the main reason that other languages haven't done this is A, it's new, but B, it makes the language harder to learn. Like, a lot of people talk about like fighting the borrow checker when you first learn the language because it is preventing things that you can do in other languages. So in exchange for like getting this runtime trade, this runtime efficiency and this safety, you have to spend more time writing the program. Yeah. Um, right. So you have the borrow checker, and so the borrow checker has two main rules, other than you can't use things after they freed. You can share things. You can like multiple references to them at the same time, or you can mutate them. You can change them, but you cannot do both at once. You can't have two things that are mutating the same variable at the same time. It's not allowed. And this is kind of like unique to Rust. I don't know anyone else that does this. And it has the really cool side effect that most things are thread safe by default. If you can't mutate things from two different threads, you no longer have data races. Because how would they race? They can only read, they can't both write. Which is a really interesting property. Um, not just access, one of them is trying to write to the memory. At the same time someone else is reading, and you get what's called write tears. So the first thread reads half of the value, the second thread writes to it, and then the first thread gets half of the new value. So now you have garbage. Because you have like half of the old value and half of the new value, and it's useless. Because you can't read and write at the same time. You can't have another reference out at the same time that you have a mutable reference. No, this right. Python has what's called a global interpreter lock, which is there's only one thing executing at any time, only one. And this means it's hard to do things in parallel in Python, and sometimes it's easier to just like launch a new process rather than launch a thread. Python is yeah. Yeah, Python is special. What was I going to talk about? Oh, right. So I was saying this is like restricting you to certain patterns of usage, right? In exchange for thread safety, in exchange for eliminating some sorts of bugs, it means there's less code that's valid to write. And so one of my favorite articles is called Learning Rust with Entirely Too Many Linked Lists. I love this article. It's so good. And it's basically about how writing a doubly linked list in Rust is almost impossible. Like you can do it, but this is like something you do after a year in Rust, as opposed to like in Java, you'd probably learn it in your second semester course in algorithms. And so the difference here is the compiler doesn't really understand this usage pattern, right? So even though you know it's valid, you know that it's possible to write this and have safe code, the compiler doesn't. So it's harder to do in Rust than it would be in other languages. And so the way you get out of that is there's a keyword called unsafe, which says, yes, I really do know what I'm doing. Let me dereference this mutable variable while someone else is looking at it. Right. So Rust is fast, and the way Rust is fast is LLVM. So LLVM is it originally stood for low level virtual machine. Now I think it just like is a phrase. And basically what it is it's a compiler framework. So it's used by all different languages. It's used by Rust, it's used by Swift, it's used by Clang. There's a whole bunch of compilers that use it. And basically what it does is you take like your code, like Rust code or Swift code or whatever, you turn it into what's called LLVM IR, intermediate representation. And then LLVM takes that and it does like magic optimizations to make your code go fast, and then turns that into a binary you can run. And the magical optimizations that make it go fast are what makes Rust fast. Rust itself does not have many optimizations. It's LLVM doing the hard work. The trade-off here, of course, is LLVM is very slow. So there's actually like a flag built into the build tool, which is release, which is, yes, actually do the optimizations because they can take so much longer than just feeding the code in unoptimized. Right, so this is the most subjective part of the talk. This is why I like Rust, is I feel like it just fits together very well. Nothing here is unique to Rust. Like parts of this are in almost every language. It has a build tool called Cargo. If you've used NPM, it's sort of like that. It manages your dependencies, it builds them for you, all that stuff. But if you compare this to the state-of-the-art in C++, which is like CMake, it is a world of difference. Don't use CMake if you can avoid it. I hate CMake. So I'm going to go on a tangent here because I hate build systems so much. The real difference between Cargo and CMake is in CMake you specify your dependencies yourself. You say this file depends on this one. Cargo just like knows automatically, like it understands Rust code, and so you can't get it wrong. Like you can't forget to add a dependency because they're like, oh yeah, that file exists. Whoops. Cargo knows the file is there. Like it picks it up automatically, which I think is a really cool feature. Rust has first-class documentation, which I actually work on. I work on the open source Rust doc project. And basically this is just like a tool that takes your code and it generates like HTML documentation from it, which gets hosted on a site called Docstar.rs. And so this is really neat. It's sort of similar to read the docs in Python, but the difference between this and read the docs is that it gets generated automatically. You don't have to set it up yourself. You just like publish your crate. Let me find a good example. And Docs.rs will automatically build your documentation for you, which is really cool, I think. And it looks like reasonably nice. Like this isn't, like there's probably documentation that looks better, but this is pretty nice. It has their standard formatter. If you've heard of Go format. This is pretty similar to Go format. That said, I really hate Rust format, and I think it's bad, but it's the alternative is not using Rust format, so what are you going to do? And then, so this is hard for me to describe if you've never used Rust, but one of the things I like about it is how things fit together really well. Like, you have this sense that instead of like one-off like special cases, things build on each other really well, like independent features come together. And so one example I'm going to do is the add trait. This is how you do operator overloading in Rust. Is there's like a trait you implement. So now I have to explain traits. If you've done like interfaces in Java or interfaces in Go that say, I want any type that does these things, that's what traits are. Traits are a way of like sharing code and saying, okay, I need this property, and I'm going to be generic over that property. So this is the add assign trait. And so the interesting thing about this is it's just a normal trait. Like you take this and you implement it for your type, and now you have operator overloading. And the way you would do this in like C++ or Python is you would have like a magic function you implement, like operator plus, or like I think underscore add in Python. And it's kind of like compiler magic. To figure out what these are, you have to Google, okay, Python operator overloading. And every one of them is its own special case, sort of. In Rust, you go to standard ops, and they're all right here. This is the canonical list of things you can overload. Well, there's a lot of documentation first. Yeah. This is the canonical list of things you can overload, which I think is cool. Like this just kind of emerges from traits. The second example I want to give is unit tests. I have to find the Rust book, and I'm starting to have far too many tabs open. So Rust has unit testing as like a first cast thing of the language. It's not so in Python. PyTest is like a separate library you add. Like you write your code, and then you install PyTest, and then you like write your tests in a separate file, right? In Rust, you like put them in the same file. Like the compiler understands them. You can say, okay, I want to do this thing differently in tests only. If I could find it, I think this is the section. This is a long book. That's the other nice thing about Rust is it has lots of documentation, but the issue is it means there's lots of documentation, so I have to read through all of it. Right, so here's like how you'd write a simple test in Rust. So this config here, if you've heard of like if-defs in C, I don't know if there's an equivalent in other languages. But this is basically conditional compilation. I want to compile this if some property is true. So the property here is you're testing the code. And then you just write a function, and that's basically it. Like there you go. So it's very nice, and Cargo makes it even nicer because you just run like cargo test or whatever. Let me find a project. And like that's it, and you're up and running. Oh, well, it's going to take a while to compile. So that's the other thing I don't like about Rust is the compile times are awful. It doesn't help that I'm also video streaming at the same time. But right, so the next thing I want to talk about is like who is using Rust. Like I've said all these nice things. Like is this just someone's hobby project? And the answer is no. There are actually quite a lot of companies using Rust. There's Amazon, there's Microsoft, Firefox was one of the first to use Rust. All these companies, on and on and on. And the reason they're using it is mostly for the memory safety. Like all the nice things I've talked about, the programmers who use them like them, but the reason the companies are using them is because of the memory safety. Because the alternative is using C++. And if you look at like the history of Firefox or Windows, I think something like 70% of all their bugs are just from memory safety. So this is a big deal to them that they can get this performance and get rid of like this whole category of bugs at the same time. All right, but the real reason to use Rust is it has great Ferris emojis. All right, thank you everyone. I'm happy to take questions. If there's no questions, I can go on and like show some real world examples of Rust code. Yes. Yeah, so there's two reasons. One was a former ACM member actually gave a talk about it, and I got interested that way. And the second is I took Fenner's compiler course, and I really like compilers, and I wanted to write my own. And I tried writing one in Haskell, and it went very badly, so I decided to write one in Rust instead. And that went pretty well. Yeah, Haskell is weird because it doesn't allow you to do I/O in any function. Like if you want to do a print line, you have to bring it all the way up to the top level of your program, and it's really annoying. So. Oh boy. Not ideal, yeah. Right. Yeah, Rust has that same property. Is if you get a seg fault, you know it came from an unsafe block, and you can look just at that unsafe block instead of at the whole program. Yeah. Other questions? Yeah. So I'm realizing that I did that whole talk and I showed like one example Rust code. So we're gonna take a dive. This is a project I work on in my spare time. I do a lot of work with documentation in Rust. So and basically what this does is it compiles your documentation. It looks at the generated HTML files and it says, "Oh, are there any broken links here?" Which is it's conceptually a very simple program. Okay, so let's take this a line at a time. So these are imports. This says use these parts of the standard library. I don't know what this is doing. So this is a doc comment, but I don't know why it's here. Oh, well that's, huh. Apparently this is a link to get user media. Okay. Anyway, so these are imports. This is the standard library. These are some other libraries. So I didn't talk about crates.io. So crates.io is like where user... so I have to say what a crate is first. So in Rust, the structure of a program is basically like you have files, and then you have, well, modules, really. So you have a module, which is like where your functions and your types and all those things go. You have a crate, which is like all the modules put together, and a crate is like the unit of compilation. When you say rustc some file, it's compiling one crate. And then you can depend on other crates. And so the crates.io is like where other people upload their libraries for you to use. And so I'm just going to pick like a random common library. So this is rand, it generates random numbers, and it has a version and all these things, right? And so Cargo makes this quite nice, because if you look at, so this is like the configuration file for Cargo. And this one's more complicated than it really should be. Where did rand go? Oh, I don't actually have it. But the way you say add a crate to my project is you just say, okay, I want this crate at this version, and then Cargo builds it, which is useful. Right, so we have this crate that we're using. We have log, we have Ryan. Ryan is like a way to do multi-threading really easily. You say, I want to do these things, and I want them to be in parallel. And Ryan takes care of the do it in parallel bit, which is very convenient. So let's take an example of what that looks like. This one thing here, parallel bridge, this says, okay, take all these like tasks that I have, right? So this is like a list of directory paths, like file names. And it says for every one of those file names, spawn a thread and make sure that we could read the file, make sure that it is a file and that it's like an HTML file and not something else, and like execute this function for it. So I'm not actually doing any like work to make sure that this is parallel. Like I literally just did this one function, which was parallel bridge, and now Ryan takes care of all the threads for me, which is really nice. And okay, so let me talk about send and sync, because I didn't do that before. Send and sync are how the compiler enforces that your code is thread safe. Send means you can take this value and you can send it to a different thread. Sync means you can take this and it can be synchronized between threads. You can use it for multiple different places. And so let me find, there was an article about this a while back. This guy also writes really good blogs. I recommend him. So this is about code that is thread safe, but like for complicated reasons, and it's code that you probably wouldn't write in C++ because the reason it works is complicated. And I'm not going to go into the whole program because it has like mutexes and stuff, but the main thing here is that the compiler is enforcing that this program is thread safe, or otherwise it wouldn't compile. All right, so we have Ryan, which is like a way to do things in parallel. We have like a URL parsing library, and this is like a library that finds directories in parallel quickly. So this is another module. I didn't talk too much about modules. They're normally in different files. Oh, if I could type. And this says, okay, the module check exists. Go load it and compile it. Or sorry, this says the module check exists. Load it and compile it. This says import one of the functions into the current namespace. So if we look here, is available is just like a function available in that module. And it does a thing. So right here it's saying, okay, is this link broken? And if it's broken, then it returns an error. Otherwise, it does nothing because you're going to go on and keep on checking more links. And so derives are interesting. Haskell has derives. I don't know if other languages have them. Basically, what this says is I want you to take like this common functionality, like comparing two objects, and I want you to write the code for me, literally write the code for me. And so if you imagine like you have a struct in C and you want to compare it to another, you have to write like struct equal, this field equals, and this field is equal, and this field is equal. In Rust, like you can just say derive partial equal, and the compiler generates that code for you, which is really useful. Let me see if I have cargo expand installed. It might take a second. Oh, great! It's recompiling everything. But cargo expand like shows you the code that the compiler is generating. The other cool thing about Rust, which I didn't talk about much, is enums. So in C, an enum is like just like a list of integers, right? Like they're named. There's a set like fixed list of them, and that's about it. Like it's just a list of numbers. In Rust, enums can actually hold data. So I was talking about option before, which was like the alternative to null. And so option is defined as an enum. Either it has some value or it has no value. But this sum option is like, it's one of the enum variants. You can't get this data without checking it. So this variant has a field. If you've heard of tagged unions, it's the same idea. And so let's take a look at how working with enums works. So this is like is sum, does the data exist, is it non-null? And the way this is implemented is matches makes this annoying. Hold on. My computer is trying to do too many things at once right now. It doesn't like me very much. Okay, cool. Right, so the way you'd normally use an option in Rust is you'd say, okay, match this option. If it's sum, then do this thing. Otherwise, do this thing. And so you see here that the data is like part of the value itself. Right. It has structs like you would in C. It does not have inheritance. It does not have classes. So in Rust, if you want to do inheritance, you would use like composition or something, or maybe you'd use traits. But it does not have a direct analogy to inheritance. Yeah. Yes. Yeah, it's an algebraic data type. It has no more overhead than checking for null. It has to say which one of the variants is this. Is it none or is it some? But that's it. That's the only overhead. Mm-hmm. Mm-hmm. It depends what LLVM does. A lot of questions about optimization depend on what LLVM does. I would expect if you have like a lot of different variants, it would compile that to a jump table or something where it's like branching to a specific part of the code instead of checking them one at a time. But it depends how it's optimized. Well, that's the interesting thing, is it's kind of both. I describe Rust to people as like a weird mix of C++ and Haskell, because it gets you the type safety of Haskell, but it has like the syntax and the runtime semantics of C, of C++. Well, it wasn't really assembly. You don't have to do assembly in Rust unless you want to. But the so I actually came from like an object oriented, like Python is my most familiar language after Rust. And so it was kind of a jump from Python, but not because it was imperative, it was because it's expression oriented. So if you look at this function here, there's no return statement, right? This little oh well, hold on, let me find a function that returns something. All right, cool. So notice, oh, this has a macro. Boo. Why is Rust? Okay, here we go. Yeah, it does return, but it doesn't do it returning using the return keyword. So this is just the expression, not self.isSum. But because it's the last thing in this block here, that means the whole block has the value of that expression. And so this is really common in Rust, is you don't write the return keyword unless you have like weird control flow with loops or something. Most of the time you just have like an expression at the end of a block. Let me find a good example of this. And feel free to ask other questions in the meantime. It'll take me a sec. Yeah, from Jeremy Day. I think so. I don't know if he's still at Facebook. Hold on. Wait, no, stop. I don't want to highlight this. Mm-hmm. So this is another interesting example. I have return, and then I have this whole expression, right? So the whole thing about expressions at the end of the blocks have the blocks have that value of that expression. That's true for any block. So this whole if-else statement has a value, and so this return says return the value of the if-else expression. So if, yeah, go ahead. No, so that's the other common thing people run into. This is not the last thing in the function. This is the last thing in like a different block here, right? So this is like assigning a variable up here. If some condition, then like it's this thing. Otherwise, return this, right? So nothing below this gets executed in the else case. So you need to return. Does that make sense? So this is, yes. Yeah, so this is shorthand. Sorry? Yeah. So that if-let here is another thing that's kind of odd coming from other languages. So that is shorthand for this guy here. And so basically it's saying, okay, if that condition is true, do a thing. Otherwise, just do nothing. And so we were comparing that to if let. So these are doing the same thing here. It's just syntax shorthand. All right. Yeah, so what this is doing here is this is an option, the alternative to null. And it's saying, okay, match this option. If it has a value, if it's not null, then do a thing, right? So let's say we're going to print it. I don't know. Why do I always end up live coding? It's awful. I have a terrible habit. Okay. Right, so this is like, if it has a value, then print the value. So the value was 1, so it printed that. And this is doing the exact same thing, but like shorter. Because we have like... No, it looks weird. This is a pattern here, and this is the variable you're matching on. The expression you're matching on. No, you're good. It's flipped. It's kind of odd. Yeah, pattern matching is interesting. Pattern matching is actually really flexible. So you can say, match this if the inner value has some property. So here, if it's 1, right? And then, oh, right, so that was the other thing that was going on here, is this is binding a new variable in the current scope. So it's creating a new variable called x with the inner value, and it's printing that. And so when I change this to 1, it's no longer binding x. So I'm going to do something else. Right. And it has some other value. What was that? Sorry? Can I match things inside of some? No, I can't. Yeah, I can't match x plus 1, but I can't do x if x plus 1 equals something. Yeah, yeah. Okay, yes. Okay, I see what you're saying. Yeah, you can do that. Yeah. Match it if the value is 1 and name it this thing and bind it to a variable. Yeah, that works. Yeah, the @ symbol. Mm-hmm. Right. Rust has lots of warning. It's big on the compile time bug catching thing, yeah. Yeah, one of the big differences between Haskell and Rust is Haskell does not have exhaustive matching. And what I mean by exhaustive matching is if I comment this out and I don't have the none case, right, then it actually gives you an error. It says you have to handle this. If you don't, like, something went wrong. And now you can handle it by doing nothing, which is what this does. But say you had a more complicated expression, like, so you remember that all blocks have an expression, so I'm going to assign a value to this expression. So match 3, right? And so if it's 1, I don't know. Maybe we'll do powers of 2. If we imagine if the compiler didn't catch that we hadn't handled cases, then you would basically have uninitialized memory. There was actually a bug because of this a while back, is the compiler didn't catch this case. Well, it's not on my browser history, but if the compiler doesn't catch this, then Y would like basically be uninitialized memory. So this has to be exhaustive in order for the program to keep working. Now, the way Haskell handles this is it just like crashes the program. Like it says you didn't handle this case at runtime, but Rust is big on compile time stuff. So. Right. 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 All right. Questions about this before I go on? Okay. Right, so these are more traits like I was talking about before with operator overloading. They don't have to be for operating for operator overloading. This is just a normal trait. And it says this is like the way to default construct a value. So if you've done C++, that like the default constructor for C++ is the same sort of idea. This has more derives, it's more structs and stuff. Vec is like a contiguous, dynamically resized array, sort of like standard vector or ArrayList in Java. Display is like how you show things to a user. It's another trait. And these are like normal functions. So these little brackets here, the pipe symbols, means a closure. If you haven't used functional languages, this might be new. A closure is like an anonymous function that can use variables from its surrounding scope. So dir path here is like a path to a directory, but it's notice how it's like from this function, but it's being used inside of the closure. And this closure is another function. So what's happened is it's actually capturing that value from the outside, and you can use it from within the closure. And closure, I think, is from close over the value, because you can like use it from here. It has a long history. It's not super important. Oh, so this is interesting. Variables in Rust are immutable by default. You can't change them. If you want them to be mutable, then you have to say, okay, I want this variable to be mutable. So this is saying, okay, I want to change this error. Nothing, it might look like nothing is being changed here. The change comes from short and all. So this is a function down here. In Rust, the function has to distinguish between whether it wants to take an immutable or mutable value. And this is like a compile time property. You can just look at it and say, okay, I know this function is going to change this value because it's in the type signature. And so you see here, it's like setting some field of the struct to a value. Yeah, so pass by reference is a thing from Java, and Java needs to distinguish these two because the syntax for them is the same. Like, so let me think how to explain this. In Java, you don't know if something is being passed by reference or by value because it's not in the type signature. Like you just see it takes like self or this. I forget what it is. In Rust, it's explicit. Like you could have this and mute, which says takes a mutable reference, or you could have just what's another one? Like does this have in self somewhere? Yeah, this says it takes an immutable reference, or you can have it take things by value, which is just don't write the ampersand there at all. And so the Java equivalent is you're passing references by value. You're taking a reference, right? But you can make copies of the same reference and pass it all over. So let me give an example of that. So like say we have some variable x, right? And you have a pointer to it, right? So this has the type i32. You can have like a whole bunch of copies of this. And you can use them all. And so these are all references to the same value, but they're copies of the same reference, if that makes sense. Yeah. Yeah. All right. I'll go on if there's no more questions. I guess we're getting close to time. Oh, so this is my favorite comment that I've written. The syntax here is so bad. This says a closure. Okay, hold on. Okay, so this is a function called reduce. I'm passing in a closure which always returns the value false, and a closure that takes two variables and returns whether either of them are true. And it ended up with literally 6 pipe symbols in the same line. It was awful. Absolutely terrible. And so notice these are doing different things here, right? Like this says a closure with no arguments, and this is like logical OR. This is bad syntax. Most Rust doesn't look as bad as that. Yeah. Oh, so this is a fun ambiguity. Hold on. At one point, if you had... Here we go, this is it. If you have 2 ampersands in a row, is that logical and? Or is that 2 references? And it turns out at one point the Rust compiler changed its mind, and changing its mind, of course, broke code, which is hilarious. But this is a long way of saying that other languages have this problem too, just maybe not in a way that looks as silly as the example I gave. All right, I think we are nearly at time. Thanks everyone for coming out.